Okay. So where did we leave off last time? What did we do? What were we talking about? Titration curves, exactly. All right. And which one did we do? Yeah, we did strong acid, strong base. And that's what we have here. Okay, let's shrink this down so it actually fits. There we go. And again, what we said is that you have all the equipment necessary to calculate the pH at any point along this titration curve. So what we did then is we started to talk about a weak acid strong base titration curve. In this particular case, instead of titrating 1 millimole of a strong acid, now we're titrating 1 millimole of a weak acid. And in this case, it's acetic acid that we're looking at, but it would be applicable for any weak acid. All right. And one of the primary differences that you need to pay attention to is the fact that if you're doing a weak acid with a strong base, as we have talked about before, the net ionic equation is different. Okay, because the conjugate base figures into the net ionic equation. We write the weak acid in its associated form, and as a result, when we write the net ionic equation, the conjugate base is a product. And what that should be for you is a tip-off that the conjugate base, excuse me, plays a role in this that isn't true for the strong acid, strong base titration. All right, so what we can say then is just like with the strong acid, strong base titration curve, let's use different colors. If I start with 1 millimole of my acid, to reach equivalence, I have to add exactly the same quantity of hydroxide ion. All right, so just like with the strong acid, strong base titration, both of my reactants are consumed. All right, but the other thing we have to account for, we'll form a millimole of water, but what's important to us is this, it's the fact that we also form 1 millimole of conjugate base. And so what we end up with in this solution is conjugate base alone. So what kind of solution do we have? We have a solution that contains conjugate base. What kind of solution is it? Is it neutral? Is it okay, it's basic, but how would we treat it? If we were going to calculate the pH of this solution, as we have talked about, and as you need to be able to do for a week from today, what kind of solution is this? Is it a strong base or is it a weak base? What's present in here that makes the solution basic? Is there hydroxide ion from excess sodium hydroxide? No, it's all gone. So what's left? You got some work cut out for you. You need, at this point, you should be able to identify this solution based on what you learned in the last chapter. It's essentially a solution of sodium acetate. What kind of solution is that? Strong acid, strong base, weak acid, weak base, or buffer. Which one? Yes, that was painful. Okay, yeah, this is a weak base solution. And what that means is that the pH of this titration mixture at equivalence is going to be greater than 7. That's what it's telling us. So there's a primary difference between the two types of titrations. In a strong acid, strong base titration, you have a neutral pH at equivalence. In this scenario, you have a weak base. Okay, now let's step back. If we start with 1 millimole of weak acid, to reach half equivalence, we're going to add exactly half as much hydroxide ion. And so in this particular case, the hydroxide ion is the limiting reactant. And again, we just conveniently overlook the water because in terms of our interest, there is none. Okay, it's there. There's lots more of it around. All right, so what kind of solution do we have here? Now we have a solution that contains, let's use a different color, half a millimole of conjugate acid and half a millimole of conjugate base. What kind of solution is that? Yeah, it's a buffer. All right. And you can see this is a special kind of buffer, as we've talked about before. But even if you didn't go exactly to half, you'd still have a buffer because you'd have appreciable quantities both of conjugate acid and conjugate base. All right. But the other thing that's true, and this is something you want to remember, at 1/2 of equivalence, as we have here, what's true about the pH of this buffer? If I have equal quantities of conjugate acid and conjugate base in a buffer, what's the pH of that buffer? No. How do you calculate the pH of a buffer? What equation do you use? The Henderson-Hasselbalch equation. And if I plug 0.5 over 0.5 into the log term, what does that give me? What's the log of 1? 0. So that means the pH is equal to the pKa plus 0, which means the pH is equal to the pKa. All right. The most common mistake that people make here is they tell me that's true at the equivalence point. No, it's not. It's true at half the equivalence point, not at the equivalence point. All right. So again, that's different. What it means in the context of this titration is that we start out with a fairly low pH, not as low as the strong acid, strong base titration. You add a little bit of base, that pH jumps, and then it levels off because you're in the buffer region, or what's known as the buffer region of the titration curve. All right. What if we go past equivalence? And again, we'll go way past equivalence. So in this case, we add an excess of hydroxide ion. And that changes our limiting reactant because all of the acid is consumed. So what do we have here? We have a solution that contains excess hydroxide ion as well as conjugate base. What kind of solution is this? What did we say about this before? We have two things that are going to contribute to pH, but which one dominates? Which is the trump card, if you'll pardon the term? Sorry? Yeah, H plus? OH minus, right? So what kind of solution is this? Yeah, it's a strong base. All right, so what that means is if we're going to calculate the pH of this solution, we're going to figure out what is the concentration of hydroxide ion in there, what's the pOH, and what's the pH. All right, so that's kind of your general roadmap of this titration curve. Now we can look at it in the same light. And actually, this was computer generated given the Ka and Kb values for acetic acid. But just like with the previous example, what we're doing here is we're titrating 25 milliliters of 0.100 molar acetic acid with 0.100 molar NaOH. And so what we would expect, given that, is that the equivalence point would come at exactly 25 milliliters of added base. And again, using what we have learned, both in this part of the chapter as well as previously, we can calculate the pH at any point along this titration curve. There's nothing new. All right, now we could draw out a roadmap as well. It's a little bit different. It's more complex than the strong acid, strong base titration curve. And so to start with, what do we have? We have a solution that is a weak acid. You can calculate the pH of that solution the way you calculate the pH of any weak acid solution, which means, of course, you need to have a Ka value. As you progress, you see what happens. First of all, you do see a little bit of a rise in the curve, and then you end up in the buffer region. All right, and when you're in the buffer region, adding more base is going to raise the pH, but not markedly. Okay, the pH goes up slowly. The other thing that's true is that at half equivalence, which in this case would be roughly here, what's the pH equal to? Yeah, the pH of this titration mixture at half equivalence should be equal to the pKa of the weak acid. Okay, what do we have at the equivalence point? We have a weak base. Right, and you can see that here because the pH of the titration mixture at the equivalence point is above 7. Right, and so one of the other things you have to be mindful about is if you're going to be using a titration like this for analytical purposes, you need to choose a different indicator than you would for the previous example because your endpoint's going to come at a higher pH. Right, and then once you get beyond the equivalence point, what do we have? We have excess hydroxide ion. and that's a strong base. And if you compare that part of the titration curve with what you see in the HCl and AOH titration curve, it's identical because the pH is based on the excess millimoles of sodium hydroxide that are present, hydroxide ion more specifically, right? But again, what you want to think about and what you need to do in preparation for exam 4 is you need to be able to calculate the pH at any point on this titration curve. Right? And it doesn't really take that much effort. It's just you have to think about things. Where are you on the titration curve? Right? What would you expect? And you can see these pH values, and they were generated by computation. All right? You can actually set up an Excel spreadsheet to do this very easily. Okay. So let's look at the third type of titration, and this is the more obscure one as far as you're concerned. The other two are far more important, although really you can deduce everything you need to for this one using the same methodology and the same calculations. If I titrate ammonia with hydrochloric acid, what kind of titration am I doing? How do we classify ammonia back in the last chapter? It's a weak base. So what we could say here is this particular titration we would classify as a weak base, strong acid titration. All right, we've got this weak base and now we're adding strong acid to it. If we write the net ionic equation for it, it's very simple. The hydrogen ion comes from the strong acid. The ammonia is the weak base. The base acts or accepts a proton. Okay, and you form ammonium ion, which is the conjugate acid of NH3. Okay, so let's do exactly the same thing we've done before. Let's start with the equivalence point. If I start with 1 millimole, except I'm doing this all wrong. Gotta do this backwards. If I start with 1 millimole of ammonia, let's put that in there first. Then it's going to take the same amount of acid to reach the equivalence point. That's the definition of the equivalence point. All right, so take the time to learn this language because if you don't, you're going to have a really rough time with it. Okay, and so we look at this, both reactants are consumed. And we form the same amount of product. So what's left in this solution? Your reactants are gone. What kind of solution is this? I have a solution of ammonium cation, right? Ammonium cation is the conjugate acid of a weak base. What does that tell me about the solution of ammonium cation? Is it a strong acid? Is it a weak acid? Is it a buffer? What is it? No, it can't be a strong acid. There's no hydrogen ion present here. What is it? The only thing that's present is the conjugate acid of a weak base. What is that? Is that a strong acid? How can it be a strong acid? It's a weak acid. Okay, so this particular titration is going to have an equivalence point with a pH of less than 7. It may not be a lot less than 7, but it's going to be less than 7 because you have a weak acid solution. All right, so at half equivalence, if we start with 1.00 millimoles of NH3, then we're going to add half as many millimoles of hydrogen ion. All right, we can see our limiting reactant. What kind of solution do we have here? What is it? It's a buffer, exactly. Right? It's the same scenario that we have in the previous example, except that we're approaching the buffer from the other end. We're coming down in pH as we add more titrant, as opposed to raising pH. But the same is true. At 1/2 equivalence, the pH of this buffer is going to be equal to pKa of the weak acid. How could we get the Ka for ammonia calculation-wise? What do we do? Sorry? Okay, but what if we can't find that? If we don't have the negative log of, if we don't have a Ka value to begin with, how do we get the Ka value? How can we look it up? Okay, but I can tell you right now, if you go to your Ka tables, and you should be familiar enough with them to realize this at this point. If you're not, you've got some work to do. Does ammonium ion appear on that Ka table? No. So what else could I look for? Yes, well, yeah, exactly. We have the conjugate base. The conjugate base has a Kb associated with it. So what do? Can't use the Kb directly. What are we going to do? How do we get a Ka from a Kb? Yes, you take Kw divided by Kb. All right, so you could do that here. Or you could also take 14 minus pKb, which would do the same thing. All right, so, and in this particular case, you get something times 10 to the negative 10th for your Ka value. It's small, but it is large enough that you're going to have a slightly acidic solution at equivalence. Okay, so let's go beyond equivalence. If we go beyond equivalence, that means we still have the same amount of our weak base, but now we've added excess strong acid. All right. What do we have? We have a solution that contains excess hydrogen ion from the strong acid. as well as the weak acid. Which is going to dominate? What kind of solution do we have here? Yeah, we got excess hydrogen ion in this solution, so it has to be a strong acid. Right? And you would expect this, okay? As you continue to add more H plus to this titration mixture, the pH is going to go down. It'll go down quite sharply to start with. So again, here's the titration curve. And what you could think about with this is because the Ka of acetic acid and the Kb of ammonia are almost exactly the same. Okay, depending on where you look. Some books say 1.7 times 10 to the negative fifth for acetic acid, 1.8 times 10 to the negative fifth for the Kb for ammonia. Some other books say they're both 1.8 times 10 to the negative fifth. All right. But regardless, if you look at this titration curve, and if you were to draw a mirror plane through pH 7, a vertical mirror plane, that's what you get. Okay. This lower part of the titration curve mirrors the upper part for acetic acid, and the same over here. The upper part of this one mirrors the lower. All right, so what are we doing here? We're going to take 25 milliliters of 0.100 molar NH3, and we're going to titrate it with 0.1 molar HCl. All right, and so if you look at this carefully, with the scale visible, you can see the equivalence point comes at 25 milliliters of added acid. Okay, so let's go through and map this out the same way we've done previously. All right, to start with, what do you have? You have a solution that is a weak base. All right, so in order to calculate the pH of that solution, you'd need to know the Kb of ammonia, which of course you can look up. And you'll be able to look up on an exam as well. Then, and just like with the acetic acid, except you're going in reverse direction, pH drops fairly sharply and then appears to level off because you've entered the buffer region. And again, what we can say, just like with the previous example, is at half the equivalence point, the pH of this buffer is going to equal the pKa of the weak acid. All right, so in this particular case, you'd end up about here, and the pH is about 9.25 or somewhere thereabouts. And if you expanded your scale, you could figure this out a little bit more, or a little bit more precisely, I should say. All right, you get to the equivalence point. The pH at the equivalence point is well below 7. It's about 5.4, so 5.35, 5.4 again, right? And then once you go below equivalence, you've got excess hydrogen ion in solution, and so this solution is a strong acid. And again, you can see that. So there's nothing here that you can't do. Once you've written out the balanced net ionic equation, which is easy, you don't even really have to balance it because it's 1-to-1, and you figured out how many millimoles of each component, the rest is cake. Okay, it's no problem. So that's something to think about. And you've got to be ready for that for the 4th exam. All right. So let's take a step in another direction with this. This is a titration curve. I actually generated this with an Excel spreadsheet. All right. But if you're taking lab this semester, you're going to produce something like this experimentally. In other words, you're going to take a solution of acetic acid And you're going to measure the pH of that solution, and then you're going to add small amounts of sodium hydroxide and see what happens to the pH. You're going to generate a titration curve. And one of your objectives when you do that is to determine the Ka of the weak acid. All right, so let's use this data to do the same thing. And there's one point that got left off here. Put that in there. All right, it looks something like this. But it really doesn't matter for our. So how could I figure out from this data the Ka for this weak acid? What can I do? At what point on this titration curve, based on what we've just been saying, would the pH of the titration mixture be equal to the pKa of the weak acid? Where is that? Where? Around 8? Would it be here? Really? Is the pH equal to pKa there? Is that what we said before? Go back and look at your notes. What did we say was true? Where is the pH of this titration mixture going to be equal to the pKa of the weak acid? It's not at the equivalence point. At half equivalence. Okay. So let's write it down yet again. At 1/2 equivalence, the pH of this titration mixture is going to be equal to the pKa of the weak acid. Now that's not here. Where is it? Yeah, okay, we need to do a little bit more to figure this out precisely. But roughly speaking, it's going to be somewhere in this part of the titration curve. Okay, I can see that my equivalence point appears to come at about 30 milliliters. All right. And so what I would say is, okay, if it does come at 30 milliliters, what's the pH at half the equivalence? Okay, which would be at 15 milliliters of added base. But here's what we want to think about. We have to prove this. How can we be certain? How can we be really precise in knowing exactly where this equivalence point is? It's somewhere in that part of the titration curve. We know that. Okay, we can see that from what we know already, because we would expect in a titration curve that the pH is going up very sharply at the equivalence point. In fact, it goes up at its sharpest, at least mathematically speaking, and that's a very useful thing to know. Because one of the things that we could do with this, and this is the way that it's been done for many, many years, is you could say, all right, this titration curve represents a function. And actually, you can generate the titration curve from a function. How do you get the steepest point along a curve function? Anybody have calculus? What does calculus do? How do you get the slope of a curve, of any point along a curve in calculus? You take the derivative. Right? So you could take the derivative of this function. And there are ways of doing that just from data points. And actually, what we've done in lab is we've set up a spreadsheet that will do this. Okay, so you can put your titration curve data into the spreadsheet and have it generate the derivative of this thing, okay? Now, I learned to call this a grand plot. Others call grand plot something different. All right, and actually the first time I had to do this, it was in the early 1980s, and we didn't have Excel. We had to do this all by hand. Okay, so we had to collect the data, write it in our lab notebooks, and then go back and analyze it by hand and do this kind of plot. And it wasn't that difficult to do. It was time consuming. It was difficult. And essentially, from this plot of the first derivative, okay, so basically what I'm doing is I'm plotting the first derivative, the milliliters of, or excuse me, of the pH with respect to the volume, and I'm looking for the point at which it's maximum, okay? And so this is the equivalence point. All right, now I deliberately did not expand this because this isn't the best way to do this. One of our faculty members who is no longer with us had come up with an even better way that I think works even better. All right, so if we go back to this curve, let's talk about this a little bit. Again, it involves calculus, all right? But her argument was very simple and very effective. At the equivalence point, another thing that occurs is the direction of curvature of this titration curve changes. In calculus terms, that's referred to as an inflection point. All right, so how do you determine the inflection point? You look for the point where the second derivative of the function equals 0, and that's defined as the inflection point. And again, you can do that with Microsoft Excel. I don't expect you to be able to set this up. We've already got it set up for you. So what I did was I did a second derivative plot versus the volume of added base. Okay, in a perfect world, you get something like this. With real data, sometimes it's a little more jagged than this. But essentially what you're looking for is the place where this curve crosses the origin, or crosses y equals 0. Not the origin, but y equals 0. And so if I look at this, then again, this is very precise. I expanded my x-axis tremendously to see this. Okay, and there are ways of doing this in Excel, which I hope you remember, at least if you're in my lab class, because I taught you how to do it. You can also do it in Capstone, which is easier, okay? But you can see, what's the equivalence point? Here's 29.99 milliliters, here's 30.01 milliliters. What would I say it is? I can be really precise here. I can say, all right, this equivalence point is at 30 milliliters or 30.00 milliliters of added base. All right, so what that means now is if I go back to my titration curve, I'm correct in saying, okay, somewhere in this region of it, the pH of my titration mixture is going to be it's going to be pKa. And since I know the equivalence point comes now at 30.00 milliliters, 1/2 of that is 15.00 milliliters. So essentially what I want to do is I want to do this. I want to say, okay, what's the pH at 15.00 milliliters of added base? Now, using this scaling, that's not going to work so well. I mean, I can see the pH is probably about 4.2 or so. But I want to be more precise than that. I want to be as precise as I can be with the data that I have. So what am I going to do? I'm going to have to expand that part of the scale. And I went a little bit overboard with my grid lines when I did this. Okay, so in this graph, here's 15.00 milliliters. So what I can do, let's see if I can do this gracefully, is I can draw this over. It's not so good. Over there. What's the pH at half equivalence according to this? 4.15. Every 2 lines is another one, 4.16, 4.17. So it's about 4.17. And this is stuff that you should be able to do at this point in this course. What this is telling me, okay, the pH is about 4.17. It's a little bit higher than 4.17, but we want to be precise to 2 sig figs because that fits everything else that we've got. We've only been able to measure the pH to 2 decimal places to start with. How do I get the Ka from the pKa? Or from this pH? If this is true, what's pKa equal to? Sorry? Okay, but yeah, well, let's do this one step at a time. What's the pKa equal to? Then we'll get the Ka. Yeah. So according to this, the pKa is the pH at this volume of added base. So it's 4.17. And so as was said, if we want to get the Ka, what are we going to do? We're going to take 10 and we're going to raise it to the negative 4.17 power. Keeping in mind that that tells us we need 2 sig figs for our Ka value. So what do we get? Yes. 6.8 times 10 to the negative 5th. All right, now what we used to do, we haven't done this in a while, is we used to, and actually I had to do this when I was an undergraduate, is I was given an unknown acid. I was given a certain size sample of it and told, okay, what is this acid? And this is how we did it. We ran a titration curve. We determined the pKa from the titration curve, and then we compared that to known values. The other thing you can do in addition to that is you do a molecular weight or an equivalent weight titration where you determine what is the molar mass of this stuff. And that helps. All right. So keep that in the back of your mind. Bring your notes with you to lab when you're doing the titration curve lab, because that's exactly what you're going to do. You're going to determine the Ka for acetic acid using the titration curve in this way. Okay, there are other ways of doing it using the titration curve, but I think this is the most effective and the easiest to do, as long as you know what you're doing. All right, and that's actually part of the lab. You have to explain how you did it. Okay, so let's look at some titration curve problems, and that's what we're going to do pretty much for the remainder of today. If I titrate nitric acid with sodium hydroxide, what kind of titration is it? Of the 3 types that we've talked about, is it a strong acid, strong base titration? Is it a weak acid, strong base titration? Or is it a weak base, strong acid titration? Which one? Yeah, this is a strong acid, strong base titration. All right. So let's write that down. Okay. What's next? If it's a strong acid, strong base titration, let's do a couple of other preliminaries before we move on, although it's not strictly necessary. The first one I'm going to do is I'm going to write out the net ionic equation. Okay, it's very simple. Hydrogen or hydronium ion plus hydroxide ion gives me water. Okay, now there are a couple of other things that are useful to do to start with. How can I figure out how many millimoles of acid I'm starting with? Yeah, volume in milliliters times molarity. So let's do that. If I multiply 25 milliliters times 0.115, what do I get? Okay, let's do 2.87. Or is it 2.88? 2.88 millimoles. All right. So that's what we're starting with. Okay, now another question we can ask, which probably isn't so relevant for this titration, but it is for others. What volume of sodium hydroxide solution is needed to reach equivalence? How do I figure that out? What did we say the definition of equivalence is? If I start with 2.88 millimoles of HNO3, how many millimoles of hydroxide ion do I need to add to neutralize it? Yeah, the same amount. So I need to figure out what volume of the sodium hydroxide solution will deliver 2.88 millimoles of hydroxide ion. Okay, I know the molarity of the sodium hydroxide solution, so all I have to do is divide the number of millimoles by the molarity, and that's going to give me the volume of solution in milliliters. What do we get? What's 2.88 divided by 0.101? Okay, 28.5. So basically what this is predicting is that we would need that much to reach equivalence. All right. Now again, for this type of titration, that's not so crucial. But if we do either of the other two types, which we'll do at least one of them, then it is crucial that you know this. All right. Okay. So let's go through a number of different points. And this is how I phrase these problems. Okay. Again, there's nothing in the problem that tells you what type of titration it is. You have to know that. You have to know it from what you know. All right. And again, going back to what I was saying earlier, the first thing you need to be able to do, which is more crucial for next week, is you have to be able to identify solutions. Right? I put a quiz up on Canvas that a number you didn't do in the first place, which was alarming. And secondly, most of you had a hard time with it. Okay, you got to watch out for that. Right, watch out for assignments. There's another one that was due this morning or this before class today. There's another one that's due next week on buffers. Okay, pay attention and make sure you get those done in addition to the Alex problems because it's important. Okay. So let's start out. How do I determine the pH of the acid solution before any base is added? What kind of solution do I have at that point? Strong acid, strong base, weak acid, weak base, or buffer? Which one? Strong acid. Okay, so this is a strong acid solution. And essentially the question becomes, let's use a different color. The question becomes, what's the pH of a 0.115 molar concentrate or solution of nitric acid? Okay, this is a strong acid, so the concentration of hydrogen ion is going to be the same as the concentration of the strong acid, unless you have sulfuric acid, of course. What's the pH of the solution? 0 point, okay, yeah. We can go 3 decimal places here, 0.939, and that's the only place we really can do it, because when we start introducing the base, that's going to reduce the precision. Okay, so 0.939. All right, easy enough. Let's go to the next one. Okay, now we're starting to do our titration. And so what we have to remember, first of all, is what's the net ionic equation for the titration? All right, now, according to our calculations before, we're starting with 2.88 millimoles of hydrogen ion from our strong acid. Okay, now, here's what we have to think about. In this part, what are we doing? We're adding 15 milliliters of 0.101 molar sodium hydroxide. How many millimoles is that? Okay, yeah, we'll round it to 1.52. Okay, so which of my two reactants is my limiting reactant? Yeah, the hydroxide ion, exactly. All right, so all the hydroxide ion disappears. Again, we do make 1.52 millimoles of water, but there's a whole bunch of excess there. So we're going to shorthand things and leave that. Okay, so how much hydrogen ion do we have left? 1.34? 1.36, thank you. Okay, so what kind of solution do we have here? Is it weak? Yeah, there's no anion present in solution that's going to have any effect on this. We don't see a conjugate base for a weak acid in here. And therefore, what we can say is that the pH of the solution is based on the amount of excess hydrogen ion we have. So we're still dealing with a strong acid solution. And again, that coincides with what we have done before, because what we can think about, and this is where figuring out the equivalence point helps a little bit, is you can see in order to reach equivalence, we have to add 28.5 milliliters of base. We haven't done that yet. We've only added 15 milliliters. So we're still in the strong acid region of the titration curve. And so what do we do next? We say, okay, how do I figure out the concentration of hydrogen ion in this solution? I take the number of excess millimoles, and I divide it by the total volume of the titration mixture, assuming everything's additive. Okay, we start with 25 milliliters of strong acid solution, and at this point we've added 15 milliliters of strong base solution. So we're going to take that 1.36 and we're going to divide by 40. And that's going to give us the molarity of hydrogen ion in this strong acid solution. What do we get? 0.034. Okay. We could actually go one more, but that's good enough. All right. Since we're probably going to measure pH only to 2 decimal places anyway, that works. Okay. And so what's the pH? There you go. Still really low. It's higher than it was when we started, but it's still low. All right. This is a strong acid, strong base titration. Do we need to do anything other than, or with this one, other than say what we know? If I do a strong acid, strong base titration, what would I expect the pH to be at the equivalence point? Think about that net ionic equation again. There's no excess hydrogen ion. There's no excess hydroxide ion at equivalence. So what's the pH? What's the pH if there's no excess? Come on, it's not that difficult. It's, what is it? 7, yeah. All right, we don't have to do any calculations. If we know this is a strong acid, strong base titration, that we can say that. The pH is going to be 7 at equivalence. Okay. So again, the equivalence point comes, according to our calculations, at 28.5 milliliters of added base. And so in this particular case, we've gone beyond the equivalence. Okay, we can see that because this number is greater than 28.5. Okay, remember this is, again, it's 32 milliliters of a 0.101 molar solution. So how many millimoles is that? How many millimoles of base have we added? Okay, 3.23. All right, so let's write out our net ionic equation again. Very simple. H plus, OH minus. All right, now according to what we said before, we're starting with 2.88 millimoles of hydrogen ion. At this point, we've added 3.23 millimoles of hydroxide ion. What's my limiting reactant? Yeah, the H plus. Okay, I've added an excess of base. So all the hydrogen ion is going to be consumed. What's 3.23 minus 2.88? Okay. What kind of solution is this? Yeah, this is a strong base, exactly. All right, we have excess hydroxide ion, it's a strong base. And so in order to figure out the pH, what do we have to do? We have to calculate what is the concentration of hydroxide ion. So we're going to take that excess hydroxide ion. We're going to divide that by the total volume, which in this case, we started with 25 milliliters of the strong acid. And at this point, we've added 32 milliliters of strong base. So that's going to be 57 milliliters total. What do we get? Sorry? Sorry, I didn't hear the first number. So 0.35 divided by 30 or by 57. So it's 25 plus 32. 6.1 times 10 to the negative third. Okay. Sounds good. Yeah, it's not very high, but it's high enough. What's the POH? $1.21? It's got to be greater than 2. 2.21. Sorry. Yeah. You left the 0 out. That's it. It happens. And again, that's a good reason to write everything down as well. Okay. And so what's the pH? $11.79, right? Okay, so you can see the pH to go from 25 milliliters, or excuse me, to go from 28.5 milliliters of added base, which is the equivalence point, to this point, we've added about 4 more milliliters, and the pH has shot up from 7 to 11.79. Okay, so that's how you want to think about these things. And there are different ways of approaching this. Right? And again, I have a whole bunch of worksheets that you can use for this as well that will go live on Canvas where you can practice these different things. Obviously, you're not going to do much of that until after Wednesday of next week, but we have to keep moving on. Okay, so think about that. What happened to the rest of my notes? Huh. Weird. They vanished. There should be some more. Interesting. Huh. Let's try a different place. Ooh, very interesting. Okay, I'm just going to have to do this one on the fly because I don't have anything else to work with. There were several more pages to those notes. Did they print out? Just as far as this? Yeah, okay, because I have another problem in there, right? Wonder what happened to it. All right, so you're going to have to help me a little bit with this because I need to remember what the problem is exactly. Let's see. Let's do this. Let's change this to plain. Okay, so my memory is that we're titrating. We have 25 milliliters of 0.0998 molar HF. Is that right? Okay, 25 milliliters of 0.0988 HF. And we're titrating that with the same sodium hydroxide solution we used in the last one, which is 0.101 molar. Okay, I can do the rest of it now. I remember enough. I just had to get those numbers right. Okay, so what's different about this titration versus the last one? What do we see that's different? Is this the same kind of titration? Are we still doing a strong acid, strong base titration? No. What is it now? Weak acid, strong base. Okay. So that's different. All right. So what that tells me also is that I need more information. What other information do I need? What do I have to look up? What do I have to look up? If I have a weak acid, what do I need to find? I need to find the Ka value for the weak acid, right? What is it? Okay. So the value you got was from your textbook, 7.1 times 10 to the negative fourth. Okay. Some other textbooks say 6.8 times 10 to the negative fourth. We'll just go with that and stick with it. Okay. And that's what you want to do with these things. All right. Well, again, they vary from where it depends on the source. Okay. So use whatever you have. I would say for Alex, use the ones from your textbook. But I think Alex might have its own set of tables as well. So, all right, what else do we need to know? Let's think about this. If we look at a weak acid, strong base titration curve, it's different than it is for a strong acid, strong base titration curve. It looks something like that. Okay. What's this region here over on the left? What do we call that? It's different. It's a buffer, right? So if we're going to do anything with buffer calculations, what do we also need to have? We know the Ka. What do we need to do buffer calculations? The which? What's the equation we use for buffers? Yeah, pH equals what? pKa. Yeah, so we need the negative log of the Ka. So what's that? .14. Okay. 1.5. All right. Now, there's another thing we're going to need, because if we have to calculate the pH of this titration mixture at the equivalence point, what kind of solution do we have? We have a weak base. And so we need the Kb value for HF. So to get that, we're going to take Kw, and we're going to divide it by our Ka value. Sorry? Okay. Yeah. All right. So we need that. Now, the next thing we need, how many millimoles of weak acid are we starting with? Okay. Now, let's do the same thing we did last time. And that is, what is the volume of the NaOH solution needed to reach equivalence? And so we know, based on this, we need 2.47 millimoles of NaOH. And we also know that the molarity of the NaOH solution is 0.101 molar. So what do we get? Okay. All right, so that's something, and here we're actually going to need that number. Okay. The only reason we had it last time was just to give us an idea of where we were on the titration curve at each point. Okay. So let's do the same 4 things that we did previously. All right, so we're going to start out. We're going to say, all right, so what's the pH of the analyte, which is HF, before any base is added? What kind of solution is it? Strong acid, strong base, weak acid, weak base, or buffer? If I have a 0.0988 molar solution of HF, which one of those is it? Strong acid, strong base, weak acid, weak base, buffer. Which one? Yeah, it's a weak acid solution. Okay. To reference the titration curve, we are here. So we have a weak acid solution. All right. How do we get the pH of a weak acid solution if we can approximate? We can calculate the hydrogen ion concentration by taking the square root of the product of the Ka and the starting molarity. What do we get? I'd think something times 10 to the negative third. Yeah. Oh, I'm sorry. You said, okay. 0.0084. Yeah. There we go. And so all we have to do then is take the negative log of that, and we got the pH. Sorry? 2.08. Okay. Yeah. All right. Let's get a clean page. Okay, so we want to figure out what is the pH after 15 milliliters of base are added. All right. Now, there are several ways we could approach this. Let's go back to our rough drawing of the titration curve. Okay. According to what we have already done, what we say is that this roughly here is our equivalence point. Okay. And that is represented by the addition of 24.5 milliliters of base. Okay. So we could write that here. 24.5 milliliters. Okay, if we're at 15 milliliters of added base, where does that put us? That puts us about here. What region is that? Yeah, it's buffer region. Okay, good. All right, you're starting to see this. So again, there are several ways we could approach this. That's the quick and dirty way. Okay, we know we're in the buffer region. Let's prove it. Okay, we'll prove it by calculations. So here's what we can do. We can say, all right, if this is true, let's write the net ionic equation for this titration. Now we have a weak acid. The weak acid remains associated. We add hydroxide ion to the weak acid, and we produce water plus the conjugate base. Okay, now remember what we said before. This is 15 milliliters of 0.101 molar. And so that equals how many millimoles? We actually figured it out once before. 1.52? Or is it 1.52? I thought it was 1.52. Yeah. That, by the way, that small change isn't going to make a whole lot of difference in your final answer. Okay, you round it one way or round it another. It ends up not making a whole lot of difference in what you end up with these things. So, don't be really fussy about that, and I won't be either when I look at these things. Okay, so according to what we figured out on the previous page, we're starting out with 2.45 millimoles of HF, right? Oh, thank you. Right? And now we've added 1.52 millimoles of base to this. And so the base is definitely the limiting reactant here. So what do we have left? We have a solution that contains 1.52 millimoles of conjugate base and 0.95 millimoles of conjugate acid. What kind of solution is it? It's a buffer. Yeah, okay. We've proven what we said before. This is a buffer. And so we want to get the pH of this buffer. We just plug things into the Henderson-Hasselbalch equation. 3.15, is that what we said? Yeah, 3.15 plus the log of 1.52 divided by 0.95. So we would expect this buffer, because we're beyond that halfway point, we would expect this buffer to have a pH of greater than 3.15. Okay, so that fits. Okay, what do you think is next? We want to figure out what is the pH at the equivalence point. What are we going to do? Okay, now, there are some shortcuts that you can take here. You got to be really careful, though. All right? Got to be really, really careful. But here's what we can say. Given the nature of this titration, what do we have, or what kind of solution do we have at equivalence? We have a weak base solution. How do we know that? Well, let's write out our net ionic equation again. HF plus OH minus produces H2O and the conjugate base. Now, according to our calculations, if we start with 2.47 millimoles of HF, to reach equivalence, we have to add exactly the same number of millimoles of hydroxide ion. Okay, so there's no limiting reactant here. Both the reactants are consumed. And so, what do we end up with? We end up with a solution that contains 2.47 millimoles of conjugate base. Okay, now, there's no reason you have to do this. All you have to do is say, okay, at equivalence, if I start out with a certain number of millimoles of conjugate acid, I'm going to end up with that number of millimoles of conjugate base. Right? So really, you could just shorthand this. You could say, okay, at equivalence, I'm going to have 2.47 millimoles of fluoride ion here. Okay, but here's the thing. This alone is not going to help me determine the pH of the solution. What do I have to be able to do? This is a weak base solution. So I have to figure out what is the molarity of this conjugate base. And in order to do that, what do I need to do? I need to take the number of millimoles that are present and divide it by the total volume. Okay, so what did we say? Let's go back and make sure I've got these numbers correct. I said that I need to add 24.5 milliliters of base solution to reach equivalence based on our calculations. Okay, so the total volume of this solution is going to be 25, the volume of the acid solution we started with, and is it 24.7, 24.5? I said, thank you, 24.5. Again, that small discrepancy wouldn't make a huge difference here in the molarity, maybe a tiny one. What's the molarity of the fluoride ion? Yeah, 2 sig figs will do fine. Okay. Okay, and the reason we can get away with that is because, again, we're gonna have to limit the sig figs based on the Kb value anyway, right? Okay. So essentially what this becomes now is, all right, we've got a weak base solution. And what we need to do is figure out what is the pH of this molarity weak base solution. And we said the Kb was 1.4 times 10 to the negative 11th. So if that's true, which I have no reason to doubt, the concentration of the hydroxide ion, if we can make the approximation, is going to be the square root of the Kb value, 1.4 times 10 to the negative 11th, times this initial molarity, which is 0.050 molar. So what do I get for a hydroxide ion concentration? Okay. And from that, again, what we have to remember is we're going to get the pOH. So what's the pOH of this titration mixture? Okay. 6.08. And so the pH is 7.92, right? Okay, so you can see it is above 7. It's not a whole lot above 7 because fluoride ion is not a very strong base, but it is above 7. All right, so that's the most complex part of this. And again, it's safe for you to expect to see this on the 4th exam. And the other thing, the other place it's safe for you to expect to see this is if you are in Chem 126, you're going to see this in the titration curves lab because you have to do the same calculation. All right. So we're just going through the same set of, so now we're going to add 32 milliliters of titrant. What do we get? Well, again, let's map this out. What do we see? The net ionic equation has not changed. Okay, if we're adding 32 milliliters of 0.101 molar sodium hydroxide, what's that? That's 3.23 we said? Okay. So if we start with 2.47 millimoles of HF, we add 3.23 millimoles of hydroxide ion. That means the HF is going to limit this. So I now have a solution that contains 2.47 millimoles of conjugate base. But in addition to that, I also have 0.76 millimoles of excess hydroxide. So what kind of solution is this going to be? Strong acid, strong base, weak acid, weak base, or buffer? Yes, it's going to be a strong base. We've got that excess hydroxide ion. That is the dominant feature of the pH of this solution. So what we can do then is we can say, all right, the concentration of hydroxide ion in this solution is equal to the excess millimoles divided by the total volume. Point 0.032? Oh, 0.012, okay. 1.3, that's okay. All right. And so from that, we can determine the pOH. There we go. Okay. So we got a little more time. I don't think it's prudent to start the next section. I think I'll wait. I'll hold off on that until Monday of next week, right? So let's look at some more problems along these lines. All right, what I'm going to do is I'm going to pull up the worksheets that we have used or that we use. And again, you'll have access to these on Canvas. Oh, crud, that's right, these things disappeared. All right, I'm going to have to look somewhere else. Somehow, some of my files got messed up. Let's see, chapter 17. There we go. Okay, there we go. Let's skip this one. I'm going to do something else. Or not that one, not that one, not that one. Ah, here we go. This is the one. Okay. So let's go to the third type. We won't finish this today. I'll probably finish it up on Monday, or you can try it on your own. We're titrating 0.114 molar solution of ammonia with 0.101 molar hydrochloric acid. What kind of titration is this? Strong acid, strong base, weak acid, strong base, weak base, strong acid. Weak base, strong acid, right? Okay, because the ammonia is a weak base. All right, so let's write that down. Weak base, strong acid titration. All right, what's next? What do we have to look up for ammonia in order to do this? Yeah, let's find the Kb value for ammonia. What is it? Yeah, 1.8 times 10 to the negative fifth. Okay, now, given what we saw the last problem, what other information do we need? We have the Kb value. What else do we need in order to do this? Let's think about this titration curve. What features do we have? Okay, we're starting out with a weak base solution. The pH is going to go down, then it's going to kind of level off. That's a lousy job of doing that. So drop, and then something like that. So what else do we need to have? Yeah, we need the Ka. All right, so let's figure that out. So we're going to take Kw. We're going to divide that by our Ka. what do we get? Something like 5.5 times 10 to the negative 10th? 5.6, okay. All right. What else could we use in here? If we're going to look at any components of this titration curve before the equivalence point, what region is that? What did we say before when we mapped this out? This is a buffer, right? So not only do we need the Ka, we might need the pKa. So let's figure that out. What's the negative log of 5.6 times 10 to the negative 10th? Yes. Okay. So we got everything. All right. Oh, actually, we're working on it. We still have a few more things to do. All right. How many millimoles of ammonia do we have in our analyte? Okay. All right, so the other thing we can think about then is, okay, what's the volume of the sodium hydroxide that we need, or excuse me, what's the volume of the HCl we need to reach equivalence? So we're going to take that 2.85. And we're going to divide it by the concentration of the HCl, which is 0.101 molar. What do we get? 28.21? Okay, so we'll do 28.2. That'll be good for what we need here. Okay. So there we go. Just like with all the other examples, we've done the preliminaries, okay? So what you can think about is for either weak acid, strong base, or weak base, strong acid, you need Ka, Kb, pKa, okay? For all these titrations, you also should figure out the volume needed to reach the equivalence point, because it's pretty easy. These are 1-to-1. All right. So let's figure this out now. What's the pH of the analyte before any hydrochloric acid is added? What kind of solution do we have here? If I have a 0.114 molar solution of ammonia, what kind of solution is it? Strong acid, strong base, weak acid, weak base, or buffer? Yeah, it's a weak base. Okay. So that tells us we need Kb. Since we can probably approximate here, we could say, all right, the concentration of hydroxide ion that's in this weak base solution is going to be equal to the square root of my Kb. Times the initial molarity. Sorry, 0.0143. Okay. All right. One. Okay. I'm just going to go 0.0014. And again, that's because we can, you could keep that extra decimal place, but or sig fig, but again, you're going to lose it once you calculate the pH anyway. Okay. So what's the POH? 2.34? Oh, okay, sorry. 2.84. And so the pH, yes. right. Where are we? Are we in the buffer region? Are we past the equivalence point? If we add 15 milliliters of base, what do we know? Based on what we set up here. Yeah, we're going to be in the buffer region. Okay, let's prove it. So if we look at this, what are we doing? We're going to take hydrogen ion plus NH3, and that's going to give us ammonium ion. Okay. If we add 15 milliliters of 0.101 molar hydrogen or strong acid, how many millimoles is that? Yeah, 1.52. That should sound familiar by now. Okay, so we start with that. And what did we say? How many? I've already forgotten how many millimoles of ammonia. 2.85. Okay. So we're mixing that with 2.85 millimoles of NH3. And so we end up with a solution that contains 1.52 millimoles of ammonium ion. And remember, what we have to remember is that's the conjugate acid. And how many millimoles of conjugate base? Okay, so we definitely have a buffer. As we predicted. And so therefore, we can get the pH of this buffer by taking the pKa, which is 9.26, plus the log of 1.33. Okay, we've got to pay attention to what goes where here. Get that. So what's the pH of my buffer? 9.20? Okay. Sounds good. Should be a little bit less than 9.26, and that's indeed what you got. All right. I'm not sure we'll finish this, but let's give it a shot. Add equivalence. What are we going to have? We're going to have 2.85 millimoles of ammonium ion. Okay, I'm going to shortcut this a little bit. At equivalence, I'm just going to have 2.85 millimoles of the weak acid NH4+. All right, so I can calculate the concentration of that. What's the concentration of NH4+ at equivalence? We're going to take that number of millimoles and divide it by the total volume of the titration mixture. We started with 25 milliliters of weak base. And to reach equivalence, we figured out that we needed to add 28.2 milliliters of base solution. I'm trying to remember what the KB is, or Ka as well. Write it down before I forget. Okay, 0.054. All right, so we don't have as much work to do from here as we did before. We can calculate the pH directly from this. Or excuse me, we have to calculate the hydrogen ion concentration first. So assuming we make the approximation, which is a pretty valid assumption, the hydrogen ion concentration in this solution would be the square root of that Ka, which we determined to be 5.6 times 10 to the negative 10th, times this initial molarity, 0.054. 5.5 times 10 to the negative 6th, okay? Now we don't have to do anything with POH because we've already determined the concentration of hydrogen ion directly. And so all we have to do to get the pH here is to take the negative log. 5.26. Okay, that makes sense. It's not very acidic, but it's acidic. All right, maybe we will finish this today. All right, last one. All right. So we're starting with, I forgot. That's why it's good to write these things down. 2.85 millimoles of NH3. How many millimoles of hydrogen ion have we added if we add 30 milliliters of a 0.101 molar solution? 30 times 0.101, I get 3.03. Okay. So what's my limiting reactant? It's the ammonium ion. I'll set this in here too. So what do I end up with? I end up with a solution that contains 2.85 millimoles of ammonium ion and how many millimoles of hydrogen ion? 0.18. What kind of solution is it? Yeah, it's a strong acid. Okay. So all we have to do to calculate the hydrogen ion concentration is take my 0.18 millimoles, divide by the total volume. So in this case, it would be 55 milliliters. Okay. Yeah, so you see we've gone way down. And if you add more acid, of course, it'll continue to go down. All right, we're perfect. Right on time, we managed to get through that. That's pretty impressive. All right, so what you need to think about is you need to practice this. All right, and again, of course, you're not going to think so much about that until you've gotten through the next exam, but you need to practice that as well. That's what I'm seeing so far. You need to keep practicing on those things. All right, I'll see you Monday.